So when we talk about interpolation, we actually think in terms of curve fitting, okay? And for instance, in communication, we get to use this for signal recovery, okay? We want to recover particular signals. The signals we want to fit the curves. But the bottom line is, for interpolation, the interest is on how to figure out the points in between the known intervals, okay? Points, figure, let's say figure out points. In between known intervals. So the idea is that interpolation is a method used to estimate the values of a function for points that are not given. So let's assume I have a point here on this plane, then I have another point here. Now, through interpolation, I should be able to fit this curve to either trace a path to this, so meaning the particular algorithm I may have used must have evaluated these points. Excuse me. Or better still, it could be a straight line, okay? Whereby these positions or points are estimated using some known algorithms. And then you realize that, for instance, if we end up transmitting a signal, say from the transmitter to the receiver, say something like this, and at some point, we now discretize to receive something like this. So what are we going to do to recover this signal? So the technique we end up using is some techniques that will be able to approximate these points. So say, well, I haven't gotten something like this, then this should go something like this, then something like this, then something like this, to reconstruct the exact same signal. It also finds its application in power, communication, control, and some other fields. So we can therefore say intuitively that interpolation is the construction of new data points within the range of discrete set of known data. Okay? And we have quite a number of methods. Some of you must have played with regression and all of that. We won't be talking about all of those today. But today we'll be talking about just a few methods, okay? The polynomial interpolation. Then we'll also talk about spline interpolation. Then we also try to cover the Hermite interpolation. And for the polynomial interpolation, we are going to cover the Lagrange interpolation and the Newton interpolation. Why for spline, we'll try to cover linear spline, quadratic spline, cubic spline, Bezier Spline, and the Bezier Spline, usually referred to as the B-Spline. And then we'll also look this up. Now, when it comes to implementation, the Hermite technique and the B-Spline could be involved, and as such, we want to, rather than attempt them analytically, because it takes so much time due to some rigor in the computation, we'll try to implement those on MATLAB, okay? But we'll definitely play with the basic principles, okay? So one point you should take note of is that the interpolation technique is used for curve fitting, because oftentimes when you conclude your simulation and all of that, you want to get a perfect curve fitting for it. And in terms of research, oftentimes you are able to come up with your data measurements and all of that, and then you want to propose a model, okay? So curve fitting is one way to develop the mathematical model for your measured data. And as such, you are able to pull off that particular equation and then name it after yourself to say, well, this is my model, okay? In terms of curve fitting. Then you can also use this to estimate intermediate values, okay? Just like I mentioned earlier. So let us begin with polynomial interpolation. So when we talk about polynomial interpolation, it's actually the process of fitting a polynomial, say P of X, of degree n, that passes through n plus 1 data points, such as S0, Y0, S1, Y1. These are the points, S2, Y2, and S3, Y3, all the way to Sn, Yn. And the advantages of using polynomial interpolation is that it produces an exact fit for the data, okay? So it's able to trace the pattern of that data. And so it is useful when we actually desire smooth and evenly distributed path or pattern. And one of the major disadvantages is that it could lead to, oscillation for high number of points. And that's the phenomenon is usually referred to as wrongs phenomenon. Okay, so for us to be able to avoid this oscillation for large degrees of n, we now have to figure out a way to break the single polynomial into multiple polynomials. So when we get to the Bezier spline and the Bezier spline, even the cubic spline, then you see how that plays, how that plays out. Okay, now we already mentioned that we have two major examples of the polynomial method, the Lagrange and the Newton interpolation. So let us try to show the formulation for the Lagrange interpolation. So the idea about Lagrange interpolation is that we use it to construct a single polynomial, okay? Yes. Recall I mentioned when we have a single polynomial, we could run into a major challenge, which is usually referred to as the wrongs phenomenon, because when the degree extends to a large number, then we begin to see some form of oscillations. So we want to avoid that, okay? But for this, we can actually use this for the construction of a single polynomial to represent the data points, okay? And this is formulated as P of X being the polynomial, being the same as sigma I taking on values from 1 to n, which is the sum of y sub I, L sub I of x. Okay, here in this case, L sub I of x is the Lagrange polynomial, okay? And it is represented as L sub I of x being the same as pi, for which j takes on value from 0 to n, and j is not the same as I, such that it gets okay, sorry for that. So, and then we have this as the multiplication. Why this is the sum. Sigma is the sum. Why pi is the multiplication of these parameters, x minus x sub j over s sub I minus x sub j. And here you take note that j takes on value from 0 to n, while j is not the same as I. And in this case, L sub I of x is the Lagrange polynomial. Y sub j, or y sub I rather, is the known function values of s sub I, okay? So for every point, say 1, 0, for instance, 1, 1, 1, 2, 2, 2, and so on, we say that this is x naught, why this is y naught, this is x1, this point is y1, then this is s2, this is y2, this is s3, this is y3, on and on. So we are able to map all y sub I for every s sub I, okay? Where I will take on any value from 0 to infinity. And now you will also note that that the Lagrange interpolation does not require the computation of systems of equations, because what we derive here, P of S, is usually a single polynomial, just a single equation, okay? So it does not, since we are not able to generate multiple equations, so there's no need to solve the system of equations or simultaneous equation, and you should also know that it is a direct formula that is actually computationally expensive, so we also want to avoid such complexities when we try to develop the models for our data plots, or better say, figure out an approximation of our model. Okay. Now, let's see how this works. So let's assume we are given data points 1, 1, 2, 4, and 3, 9. Okay. So we want to construct P of X given this data. Now, this part is really interesting in that you are all postgraduate students, and at this point, or at this stage, you are expected to also conduct your academic research, where you are expected to propose, or something in terms of contributing to knowledge. So it means that in your research, there should be a little contribution to knowledge. And some of you may want to, conduct your research in areas where you have to go take data. Let's say for those of you that may want to research in renewable energy, probably want to go to NIMET to get their wind energy data and all of that. And then you have to plot. And then these are measured, they are raw data. Okay. And then you have to benchmark them with respect to time or with respect to some other parameter and all of that. So how do you create a model from that? So that's what we want to do here. Okay, so how do we say, well, this is the mathematical model that represents this data based on the variation. So we just plotted raw data here. And now we want to figure out the model, the mathematical model for this raw data to show that this is an approximation. Okay, so in other words, once we have this model, should the data vary, we should be able to use this to estimate the behavior, the response of the system. Okay, and now we want to apply the Lagrange interpolation method to develop these model that will approximate, or better still, provide the perfect fit for this data. Now, you will recall that P of X is given as sigma I taking on values from 0 to n, y sub I, s sub I of x, where the Lagrange polynomial s sub I of x is the same as pi, j taking on values from 0 to n, for which j is not the same as I. Then we have x minus x sub j over s sub I minus x sub j. And from this data, we already know that this is S naught, since we have our range from 0 to n, while this is y naught. Now this is x1, this is y1, this is s2, and this is y2. Now, if that is clear, then it means that L naught, when I is 0, L naught of x will be the same as x minus x1 times s minus s2. That's between this interval, divided by s naught minus s1 times s naught.
Yes, sir.
Okay.
On that polynomial equation, Li, under that pi, where you wrote j equal to y, is it supposed to be j?
It's not equal to j, not the same as I.
Thanks, sir.
Okay, thank you. So now we are now going to have x minus 2 times s minus 3 over 1 minus 2, then 1 minus 3. And now this L naught of x is going to give us x minus 2 times x minus 3 divided by 2. So the next point is to estimate the Lagrange polynomial L sub 1 of x. And then L sub 1 of x will be the same as s minus s naught, because here, when we considered s naught, you observe that here we excluded s naught because this is the same as s minus sj, for which j is not the same as 1 because j cannot be 0 when I is 0. Okay? And then we had this. So when L sub 1 of x, then this will now be s minus s naught, because when x is 1, j cannot be 1, right? So then this will now be s minus s2 over x1 minus s naught over s1 minus s2. And this will be the same as s minus 1, s minus 3 over minus 1, right? And this also L1 of s will be the same as minus s minus 1, s minus 3. And in the same vein, s sub 2 of x will be the same as s minus s naught and s minus s1, since j cannot be the same as 2. So over s2 minus s naught over s2 minus s1. And this will give us s minus 1, s minus 2 over 3 minus 1, 3 minus 2. This will be the same as s minus 1, s minus 2 divided by 2. Okay? Now that we have been able to evaluate the Lagrange polynomials, then we will now substitute into the basis formula. Okay? And we already know that this is the basis formula. Okay? So let us represent this. So we already know that P of x is the same as sigma I equal to 0 to n, y sub I, L sub I of x. So this will now be the same as y naught, L naught of x plus y1, L1 of x plus y2, L2 of x. Okay? And now we already know from our given data, 1, 1, 2, 4, and 3, 9, that y naught is 0, y1 is 4, and y2 is 9, right? So once we plug that into this, then we'll now have P of x to be the same as 1 times L naught of x, which was derived, which is x minus 2 times x minus 3 over 2 plus y1, which is 4 times, this is times, minus s minus 1, s minus 3 plus y2, which is 9 times s minus 1 over s minus 2, which will give us 2. And now this will be the same as x squared minus 5x plus 6 over 2 plus 4 into bracket minus x squared plus 4x minus 3 plus 9 into bracket x squared minus 3x plus 2 divided by 2. And here we see that this is the same as x squared minus 5x plus 6 over 2 minus 4x squared plus 16x minus 12 plus 9x squared minus 27x plus 18 over 2. And once you resolve this, you see that the basis function is the same as x squared. Okay? So this is the mathematical model that provides the best fit for this raw data. Okay? And should we decide to plot a point, say at 2.5, then with this model, we can now estimate the value for all other points that may not be given here. Okay? And that's just going to give us 2.5 squared, which is 6.25. Okay? So for every point between 1 and 9 that we now decide or desire to predict, with this model, we should be able to predict fairly. Okay? Does that make sense at all?
Yes, sir.
Okay. So now we'll move on to Newton interpolation. Interpolation. And here we have two categories, the Newton or Newton's forward difference, and also the Newton's divided difference. So when we have equally spaced points, we use the Newton's forward difference, okay? So this is applied for equally spaced points. But there are times the points are not equally spaced, okay? So we use Newton's divided difference, okay? On equally spaced points, okay? And so you see that in practice, this finds wide application, okay? So let's take them one by one. So for the Newton's forward difference, which is used for equally spaced points. So the formulation is such that P of X is the same as Y naught plus S delta Y naught plus S times S minus 1 over 2 factorial delta squared Y naught plus all the way plus S times S minus 1 all the way to S minus N plus 1 over N factorial delta N Y naught. And here we see that S is the same as S minus S naught over H, where H is the spacing between points, right? The time step, right? Spacing between points. You can also call that the step size, right? And delta Y naught, delta squared Y naught, all the way to delta and Y naught are the forward differences. Okay, so this is the formulation for this, and it's pretty straightforward and very easy to apply. Now let us define the Newton's divided difference formulation. So for the Newton's divided difference, we have that the polynomial is the same as P of X being the same as Y naught plus S minus S naught, then F of S naught S1 plus S minus S naught times S minus X1 F of S naught S1 S2 all the way, okay? And here, the divided difference is given as F of Si Sj being the same as F of Sj minus F of Si over S of j minus S of I. This is referred to as the divided differences. Now, in comparing, or by if we compare these two techniques, the Newton's forward difference and the Newton's divided difference, I think the Newton's divided difference looks a little complex. So I'll rather solve this and leave the Newton's forward difference for your practice. Okay. Now let's assume we want to play with the same set of data. Okay, using this approach. Now we've been given 1, 1, 2, 4, and 3, 9, right? This is what we played with last time. And we were able to estimate that at point 2.5, we had 6.25, right? So we're going to test this to be sure if we are getting the same approximate value. Now, we already have this as our expression. So what we now need to do is to construct the divided difference table using this expression, okay? Now, for the first column in that table, now this is, let's put the table here, X. Let me do straight line. We have X, and we have f of X, then we have this. So we have our first point, we have our second point, and then we have our third point, right? So this is f of X, which is the same as Y. And then this is the divided difference, f of X naught, S1. And then this is the next divided difference, f of X naught, S1, S2. So how do we apply this formula? Now, we already know that the first column, in this case, is the function based on the input values. So we have 1, 2, 3. So it means that at this point, f of Si is the same as f of Si, so that this will be drawn from our data, which is 1, 4, 9, which is the same as Y, right? In this case. Okay, but in our formulation, we are not playing with that for now. So just to be clear. Okay. Now, how do we now estimate the divided differences? Now, for higher order, we already know for the first column, right? So if we want to evaluate or compute the higher order divided differences, then it means that f of xi, si plus 1, all the way to si plus k will be the same as f of si plus 1 all the way to si plus k minus f of si. You know, this is si plus 1, we are now doing si minus si plus k all the way to si plus k minus 1 divided by si plus k minus s of I. So in that way, the points above this are zeros, are unknown. We don't know them. We cannot assume they are zeros. So this will be indeterminate, okay? So we can as well say this is undetermined, undetermined. Then we'll go to the next point. Here we can say 4 minus 1 over 2 minus 1. And this will give us 3. And at this point, this will be 9 minus 4 over 3 minus 2, which will give us 5. Then at this point, we'll be dealing with 5 minus 3 over 3 minus 1, which is equal to, this is how many? 2.
1.
It's 1, right? That's 2 over 2, which is equal to 1. Yeah.
1, yes.
So now we've been able to estimate these parameters, and then the next thing would be to substitute into the expression. We've been able to evaluate this, we've been able to evaluate this, and now we will now plug this into it. And we know y naught to be 1. This is y naught. This is s naught. So we already know this, and we know s naught, we know s naught, we know s1. Okay? So what are we going to get for our polynomial? So our P of X will now be 1 plus S minus 1, F of S0, comma, S1, plus S minus 1, S minus 2, F of S0, S1, S2. Okay? And then we already know these values and this. We know this is 3, this is 1. So we now have this to be 1 plus S minus 1 times 3 plus S minus 1 times S minus 2 times 1. And this will be the same as 1 plus 3x minus 3 plus x squared minus 3x plus 2. And once we resolve this, this knocks this off, and 2 knocks this off. So what we have is x squared. P of x is the same as x squared. And this is the same result we got when we use the Lagrange, right? And should we estimate P of 2.5? So we're going to get x squared, which will be 2.5 squared, will be 6.25, sorry. Now, hope you see how we are able to provide an approximation by developing a suitable model to describe or that fits the data. Is this clear? Is this clear, please?
It's clear, sir.
We are following, sir.
Oh, okay. Okay, that's fine. Now let us move on to spline interpolation.
So, sir, before you move, is there any clear difference between the Lagrange and the Newton's method where we applied it?
Yeah, definitely. There are differences because for the Lagrange, the major drawback is that, fine, we are able to estimate just one major equation, just like we also arrived at here. But in terms of computation, it is quite expensive, okay? But for the Newton's method, based on the difference evaluation, we're able to, fit the data as well with some level of accuracy, okay? But we've not gotten to the best model of approximation yet, okay? Is that okay?
That's fine, sir.
Okay. Now, for the spline interpolation, we made mention of the linear. So let's start with the linear interpolation. Now, in a linear spline, the curve is simply composed of straight line segments, okay? Between each point. So we are not able to get that perfect curve fitting, okay? So we just want to assume that all the points that are in the system are straight lines, okay? So when we use the linear spline, this is what we get. And there may be some errors, okay? This may result in some errors in the fitting of data because probably it is a curve, okay? Probably this even came this way. So probably we're supposed to get something like this, and then something like this, something like this. But with the linear interpolation, it just assumes that each point is linear. So you just it uses lines and all of that. So from this, you can already tell, what the possible challenge will be should you adopt this method, okay? And the linear spline between 2 points, say S0, Y0, and S1, Y1 is described as S of S being the same as Y0 plus Y1 minus Y0 over S1 minus S0 times S minus S0. So this is the formulation to evaluate the linear spline between two possible points. So if we're able to identify 2 points, then with this approximation, it's able to draft a linear path to that point. And should there be another point here and another point here, then we are going to get something like this. Okay? Yeah. And this may not be the perfect fit for our data anyway. So let us play with the same example for the linear spline. So we already have 1, 1, 2, 4, and 3, 9. So you want to recall that the linear spline between 2 points is given as S of S being the same as Y0 plus Y1 minus Y0 over S1 minus S0 times X minus S0. So in this case, there are 2 points, okay? The first point is between this plot and this plot, so that's 1 point. And the second point is between this plot and this plot, okay? So here we have 2 points. So we'll be estimating 2 different approximations to this graph. Okay, so we're not going to use a single polynomial or model to represent this plot. Okay. Now, so if we take for the first instance P0 to be the same as 1, 1, and then P1 to be the second point, 2, 4, for which we have 1 major point, then we can say that S1 of X, in this case, by evoking this formula, is the same as 1, which is Y. This will be Y0, right? This is S0. This is Y1. This is S1, right? So this will be 1 plus 4 minus 1 over X1, 2 minus 1 times X minus S0, S minus 1, okay? So this is going to give us 1 plus, this is 3 over 1, right? That'll be 3 into bracket X minus 1, okay? And once we open this up, so that'll be 3X minus 2, right? Yeah, because this is minus 3 plus 1, that'll be minus 2. So S1 of X will be the same as 3S minus 2. And now this is for all values of X being an element of these points, okay? Where X is 1 and 2, right? So this is S0, X1, okay? Now for the second point, we can say P1 is the same as 2, 4, and then P2 is the same as 3, 9, okay? And here, we also know that S2, this is S2 of X, will now be the same as where this is S0, Y0, S1, Y0, will now be the same as Y0 will be 4 plus Y1, this is 1, Y1 please, X1, Y1, 9 minus 4 divided by 3 minus 2 times X minus S0. S0 in this case is 2. And now we're going to get 4 plus 5 into bracket S minus 2. And here, S2 of X will be the same as 5X minus 6 for all values of S, taking values from 2 to 3. So you now see that the interesting thing or the good thing about the spline method, spline, is that we are able to generate system of equations to describe the curve. So there's every tendency to be able to come up with a better approximation for the fitted data, okay? Now, here we have S1 of x being the same as 3x minus 2 for all values of x taking on values from 1 and 2. And S2 of s is the same as 5x minus 6 for all values of s taking values from 2 and 3. Now, recall, how do we now estimate P of 2.5? Now, we're going to look at it. Now, 2.5 is not within this range. It's greater than the first plot, so we cannot use this to estimate it. So 2.5 is between this interval, so this is what we use to estimate our point for 2.5. Is that okay? And then we can say S2 of x.
Right.
Now, look at 2.5. 2.5 is greater than 2, right? So we cannot find the point 2.5 between 1 and 2 because this is, let's say, 1, 1.1, 1.2, 1.3, 1.4, all the way to 1.9, and then 2. But in this case, we can move from 2.1, from 2, 2.1, 2.2, 2.3, 2.4, 2.5, all the way to 3, right? So the plot is actually within this second interval, which describes this polynomial. So then 5 into bracket. So this will now be S to 2.5, will be 2.5 minus 6. And this is going to give us 12.5 minus 6, which is 6.5. Okay, so S, or better still P, 2.5 is the same as 6.5. Is that clear? And you observe that in our previous analysis, we got 6.25. So it's an approximated value. It's an approximate value. Okay, so well, the approximation is still not too far from 6. Is that okay? So so we now begin to look at the level of accuracy this method of approximation is giving to us. But mind you, let's assume I have my measure data and I want to develop a mathematical model to say, oh, this model from today is going to be Iraze's wind model. Okay, largely because I got raw data and I've tried to interpolate using one of the approximation to derive an equation to say, well, if the radiance is this, then once you plug it into my model, then we should be able to get this parameter for you to design your panel. Okay, that's my lesson. I just gave somebody an idea what to do in his or her project. Simple. You don't have to, you just buy time. Within 2 days, you are done with your research. Now, let's assume I decide to do that. So it means that if I should use the linear spline, I'm going to come up with 2 models that we could use for approximation for given 2 different ranges of data. But if I should use the likes of the Lagrange or the Newton's method, then I'm going to come up with just a single polynomial. And that's also fine. And we're able to run our approximation. Or better still, I could compare all the methods to see which gives the best fit. Well, and then we've conducted your research in that regard. Okay. So is this making sense, please?
Yes, sir.
Okay. So now let us move on to quadratic spline.
Excuse me, sir.
Yeah.
Before you proceed, yeah. Is it possible to have our S of 1 and S of 2 having the range of 2.5? Let's, for example, our S of 1 is 1 and 3, and S of 2 is 3 and 4. Is it possible that we'll have the range to be in that 2.5? That's just my question, sir.
We have the range between these two.
Yeah, 2.5. Let's assume our S of 1 is in the range of 2.5 and our S of 2 is also in the range of 2.5. Is it possible? And if it's possible, what do we do?
Well, going by the data plots, it's not possible because there's no way 2.5 will be in the range of 3 to 4.
Okay.
Because it's less than 3. 2.5 is less than 3. Yeah, even 2.9 is less than 3. 2.999999999 is still less than
3.
3. But when we get to 3.0, good. That may be a good point to get confused, because I have this model estimating values from 1 to 3. Then I also have this model estimating from 3 to 4. So this is the boundary. Do you get what I mean?
Yes, I mean, it's not possible.
It's possible. This is possible. I could use both of them to estimate it. Okay. And then find an approximation. But if it should be at 3.1, then it's definitely here. I don't know if you get what I mean.
Yes, I've got it.
Yeah.
That means if we have, that means possible. Let's assume we are using 3 now. That means it's possible we have 2 answers.
Definitely, because this is my boundary. This is also my boundary. And that point is just at the borderline. So we will now have to estimate to see if we will get the same value for those 2 points. I don't know if you get what I mean.
Yes, it's clear, sir. It's clear. Thank you, sir.
You're welcome. Now, let's move on to the quadratic spline. Now, for the quadratic spline, it's more like the linear spline, which is for which we're able to form piecewise polynomials, because we don't have just a single polynomial; they are piecewise. We have chunks of them, okay, and it could range from 1.
Hello, sir.
Yeah.
Hello, sir.
I'm with you. Go ahead, please.
Sorry, sir. Sorry, before you go ahead, I just want to I want you to expatiate on what my colleague just mentioned the other time. Now we have a boundary point between 1 and 3 and 3 to 4. Now we are developing 2 different models.
They are not 2 different models.
No, sir. No, what I mean is that we are developing 2 different
okay, well, two different
yes.
models
yes.
for the different points.
For 1 to 3, yes, for 1 to 3, and our point is at 3. Are you now saying we are going to specify between 1 and for the first one will be 1 and 3, and the second one is 3 and 4?
Yes.
What if the 2 of them don't agree in the result? What do we do?
If they don't agree in the result, then we'll now have to find an approximation. That's why it's an approximation topic.
Okay, sir. Okay, sir. Okay, sir. Thanks.
Now, if you look at it, everything we are doing here is all about approximation. Okay, when we talked about the initial value problem, the boundary value problem, we are iterating to converge at the boundary point, right? When we talked about the boundary value. So you now see that at some point where we already know that y of 1 is equal to 0, we now realize that when we iterate with certain method, we are still getting y of 1 to be the same as 0.009. It's not the same as 0. So it means it's not converging.
Convergent. Okay.
Yeah. So, but meaning we still need to iterate, or better still, probably at some point we may want to change our step size. You get the point? To see
yes, sir.
To see if it will converge. Okay, because by the time when we talked about shooting method, so at times we may give a particular guess, and that guess may diverge. The solution may diverge. So it means that we now have to find an approximation to that initial guess till we are able to get the best guess that we converge.
That will converge at, but okay,
exactly.
all right.
So that's why these methods are approximation methods.
The approximation methods, yes.
Yeah, that's why you see that when we have the differential equation, we want to estimate the exact solution to know what the value may be, but we know while approximating, we won't be able to get the exact solution.
Exact solution.
But the closer, the closer to it, yes. The closer, the better.
The more accurate, okay.
Yeah.
Thank you, sir. Thanks, sir.
You're welcome, sir.
Yes.
Sorry, before you continue, sir. Yes. With respect to the linear spline that we just did, we have 3 points, 1, 1, 2, 4, and 3, 9. Now, which gave us 3 linear functions.
Two linear.
Two linear functions, which is x1, s1, and s2.
Yeah.
Yes. So I am of the opinion, I'm not sure if I'm correct, that s1, which is a function between 0.1 and 0.2, whereas S2 is a function of that line. You know, we're actually going to have like two lines now. It's a function of that line between points 2 and point 3. So the S2,
be point 2 and 3. Right?
Yes, the S2 or the S1 is not a function of the 3 points because they are just functions of a line between 2 points.
And now this is it. Let me plot it. So this is my first point. It joins with this.
Yes.
It goes to this. Okay. So let's assume this is 1, 1. Then this is 2, 4.
It's 2, 4.
Then this
3,
is
9.
3, 9.
3, 9.
So it's a continuum. Okay, it's a continuum. Now the reason we attempted the cubic spline technique is because it provides the solution in piecemeal. So that's why we say piecewise polynomial, right?
Yeah.
Piecewise. So this is one piece, this is another piece. Rather than have just one polynomial. So there are times that we may have one polynomial and you see that if you just deviate and will not have huge errors. Okay? Now, probably one single polynomial may trace this path this way. Another single polynomial may trace it, let's change the color, may trace this path this way. Okay? Why another one may even trace it this way, and escape that point and go this way. But we know that by the time we are able to join the major points in piecemeal, we'll be able to get a good approximation to this problem. I don't know if you get what I mean.
Yes, so that means, okay, go ahead.
Go ahead.
Okay, that means there must be a method for us to actually combine the two linear functions together, which is S1 and S2, to give us the overall linear spline function for what for the problem we are considering.
That's what Newton did. That's what Lagrange did.
Okay.
That's what those guys did, you know, to get just one model. And we got S squared, right? And when we plotted for 2.5 an unknown point, we were able to get the same answer. Yeah. So it means that in fact, those are also good approximation. But the reason we want to revert to the piecewise models is that when the data point becomes very large, now you could have data point up to 1 million. Okay. Now having one polynomial model may not give us the best fit. But by the time we're able to join them in piecemeal, one point to another, another point to another, another point to another for the 1 millionth point, then we can be sure that it's a good approximation because all the points are plotted. I don't know if you get the point. So we're only using a very basic, simple example of 3 points. But in actual research, we are going to be dealing with huge volume of data. Maybe data that have been collected in the last 20 years. I don't know if you get what I mean. So then...
So I get your point. But the point I'm making, sir, this is it. You know, when we started with Lagrange, we moved to Newton, and we're actually getting a single value for when we evaluated when x equals to 2.5. Now, when we did linear spline, right? Just like you mentioned that it's a form of piecewise, you know, where you try to break a line into discrete pieces. Now, if you want to actually evaluate this 2.5 with respect to linear spline as well, I believe that it should actually be S1 plus S2 to give us for the whole line.
Oh, okay. I get what you mean now.
We are not taking X. S.
We are taking the linear combination of both.
Exactly.
Yes.
Okay,
now I get your point. Definitely, the graph is a linear combination of all those points.
Yeah.
Because the point is a continuum. Don't worry. When we get to cubic spline, you now see how we establish continuity. Okay, so those are conditions that must be met. Okay, yeah, I think I get what you're saying now.
Yes, that's it.
We are not dealing with different plots. We are still dealing with the same plot.
The same plot.
Yeah, they are not standalone. It's a continuum. Let's put it that way. And there's the condition for continuity. Okay.
Sorry for taking your time.
No, it's fine. It's fine. At least that must have also, educated everyone, so that's perfect,
Okay. So there's one more question I need to ask.
Okay.
When we started this course, you recommended Python and MATLAB.
Mm-hmm.
Yes. And during the course, we have been using what we call zero-based indexing, where you start from X naught, Y naught, all those kind of things. Now, if you want to implement in Python, I know that's very correct, because that's what Python uses. Python uses zero-based indexing. MATLAB uses one-based indexing.
Yeah.
Now let's assume that we are not writing program. We just want to use biro and paper in text or exam. Can we use either of zero-based indexing or one-based indexing?
Okay. You think I will ask you MATLAB-based questions in the exam, right?
No, I'm saying we want to use biro and paper, yes.
So yeah, well, I don't think it's appropriate to test coding on paper, personally.
No, I'm not saying we are going to use. No, I'm not saying we are going to use biro to write the code. Like, for example, now the equation we gave for the linear was y naught plus y1 minus y naught over x1 minus x naught into x minus x naught.
Okay.
Now let's assume that I want to write my own. Yes,
okay,
I want to write my own now, and I write y1 plus y2
okay,
minus y1.
I get your point. Now,
yes.
When it comes to your pen on paper writing, so you have to follow the indexing based on the boundaries that have been given. Okay?
Okay.
So if you specified to start from 1, then you want to start there. But if you specify to start from 0, which we usually do, then you start there. But should you decide to code, then the rules for coding subsist, okay? Because the way you declare your arrays in Python is different from the way you declare your arrays in MATLAB.
Yeah.
Okay. Yeah, because your MATLAB is built on C. Yeah, I get that point. Yeah. So that's fine. That's okay. Thank you so much. Now, just like I said, the quadratic spline is actually a piecewise quadratic polynomial that fits the points. Okay, and we can actually establish the quadratic spline between, say, points P0 being the same as S0, Y0, and then S1, Y1, for which this is P. Let me designate that correctly. Let's say P1 is the same as S1, Y1, and P2 is the same as S2, Y2. And we're saying that for the quadratic spline, we can write a polynomial equation to be the same as S of x being the same as A times x minus S0 squared plus B into bracket S minus S0 plus C. And here, A, B, C may be computed for each segment. Okay? And if we now look up our previous example, where we now have P0 to be 1, 1, and P2 to be 2, 4, and then P3 to be 3, 9, then we can say that for S of S0, then we have this to be the same as Y0, so that S of 1, for instance, S of 1 will be the same as 1, which is Y0. And in the same way, S of S1 will be the same as Y1, so that S of 2 will be the same as 4. And then S of S2 will be the same as Y2, so that S of 3 will be the same as 9. Now, if once we are able to establish this, then we can now reformulate the quadratic spline. In this case, S of S will be the same as A naught. S minus S naught is 1 squared plus B into bracket S minus S naught is also 1 plus C. Okay. Now at S equal to 1, what do we get? We have S of 1, which is the same as 1, will now be we already know that S1 will be the same as A into bracket 1 minus 1 squared plus B into bracket 1 minus 1 plus C. Okay, so this is going to give us A times 0 plus B times 0 plus C. And we know that S of 1 is equal to 1, right? So it means that this is equal to 1. So C is the same as 1. Hope that is clear. Hope that is clear. Can
Yes,
you?
sir.
Yes, sir.
Yes.
It's clear, sir.
So now at X being the same as 2, we also have S of 2. We plug that in here. That will be A into bracket 2 minus 1 squared plus B into bracket 2 minus 1 plus C. Okay. So this will be 1 times A, that's A plus B plus C is the same as 1. So we can plug that in, is the same as 4. So that will be A plus B is equal to 3. Okay. So we've been able to develop two equations. So we already know that C is the same as 1 and A plus B is the same as 3. Also, S of 3 will be the same as A into bracket 3 minus 1 squared plus B into bracket 3 minus 1 plus C, right? And this is the same as 9. So this will be A into bracket 2 squared plus B times 2 plus 1 of C is 1 is equal to 9. So this will be 4, that's 2 squared is 4A plus 2B plus 1 is the same as 9. So this will be 4A plus 2B is equal to 10. Right? Is that?
Equals to 8. 8.
Equal to 8, sorry for that, minus, right? Thank you. 9 minus is 8. Perfect. So we are good. So we have 1,
You can
2.
You can see 2 plus B equals 4.
Yes. So we can still scale this down to say we divide through by 2 and then we get what we want. Now, but the bottom line is you want to substitute all of these, which I don't think I want to do. So, and then you see that A is 1, B is 2, and we already know C to be 1. So you want to play with this in your own spare time. Those are just simultaneous equations. Now, once we do this, we cannot plug this back into the model, right? Now, we already know that S of S is the same as A into bracket X minus 1 squared plus B into bracket S minus 1 plus C. And now we know that A is the same as 1, B is the same as 2, and C is the same as 1. So here, S of S will now be the same as 1 times S minus 1 squared plus 2 times S minus 1 plus 1. And this is going to give us S squared minus 2x plus 1 plus 2x minus 2 plus 1. And here again, S of S is going to give us x squared, which is the quadratic spline function in this case. And then for us to plot our P, 205, 2.5 is pretty straightforward. And now you see that our quadratic spline approximates the solution in the same way the Lagrange and Newton's method did. Okay. Now let us go back. Okay, we've done linear, we've done quadratic, so let us do cubic spline. It is to be noted that the spline interpolation uses piecewise polynomial functions to achieve smoothness between intervals. And the cubic spline is the most commonly used, actually. And if we consider for intervals S of I and S of I plus 1, then the cubic spline may be formulated as S of I of x, being the same as S of I plus B sub I, x minus S of I plus C sub I, x minus S sub I squared, plus D sub I, S minus S sub I cubed. So the cubic spline literally ensures smoothness at the joints by maintaining continuity of the function. And its first and second derivatives literally ensures that. And based on the boundary conditions, we have two major types, the natural spline and the clamped spline. For the natural spline, this is one in which the second derivative at endpoint is 0. And for the clamped spline, this is one in which the first derivative at endpoint is specified. So if we should consider the same example, that is, given the points 1, 1, so given the points 1, 1, then 2, 4, and then 3, 9, we are expected to evaluate the cubic spline S of S, which satisfies the interpolation conditions. But it should be noted that for the cubic spline, the following conditions must be satisfied. And the first of which is the continuity of the function. Such that S of I of x must be the same as S of I plus 1 of s at each naught point. Okay? And this is to ensure the spline is continuous at the points. And then the second condition is continuity of first derivative, such that the first derivative of s sub I of x must be the same as the first derivative of s sub I plus 1 of x, still at each naught point. And the next condition is the continuity of second derivative. for which the second derivative of S sub I of S must be the same as the second derivative of S sub I plus 1 of S, still at each naught point. And then, finally, on the conditions is the boundary conditions. And on this, we have for the natural spline, for which the second derivative of S of S must be 0 at the endpoints. And then for the clamped spline, now the first derivative as specified at the endpoints. So with this, we should be able to attempt the question such that for n intervals, the cubic spline for each segment is defined as S sub I of X being the same as A sub I plus B sub I of S minus S sub I plus C sub I of X minus S sub I squared plus D sub I S minus S sub I cubed. In this case, I is the segment index, and then S sub I and S sub I plus 1 are endpoints of the segment. So in essence, we will have to solve A sub I, so for A sub I, B sub I, C sub I, and D sub I for each segment. Good. Now, if we recall the data points, that's 1, 1, 2, 4, and then 3, 9. Here we have two intervals, okay? Between 1 and 2, and then also between 2 and 3, right? Between 1 and 2, and between 2 and 3 for X sub I, right? So hence, the two intervals are for 1, 2, for S1, S1 of X, and between 2, 3 for S2 of S. So having specified that, then the next point is to set up the equations for continuity and smoothness. And for us to be able to do that, we first specify function values at naught points. So we have x1 of 1, which is the same as 1. And then we also have s2 of 2, which is 4. Then we have s1 of 2, which is equal to 4. And then we have s2 of 3, which is equal to 9. Now, this is for all s1 of x, taking on values from 1, 2. And then this is for all s2 of s, taking on values between 2, 3. And then the next thing to consider is the first derivative, continuity, such that x1, the first derivative of x1 of 2 is the same as the first derivative of s2 of 2. And then we'll also consider the second derivative, continuity, such that second derivative of s1 of 2 should be the same as the second derivative of s2 of 2, because that is the transition point. Because now we have 1, 1, we have 2, 4, and then we have 3, 9. So this is x, this is y. So these are the transition points, right? And so we have to ensure the transition between x1 and s2 for continuity. And then the next thing is to provide the natural spline boundary condition. And we already know that the second derivative of s1 of 1 must be equal to 0. The same way, the second derivative of s2 of 3 must be equal to 0. Okay? So at this endpoint and at this endpoint. So now that we have done this, we can now express the spline equations for each interval, so that we now have, for this interval, we have s1 of x, and for this interval, we have s2 of x. So that for s1 of s, we're playing with the interval 1, 2, and for s2 of s, we are playing for the interval between 2, 3. Okay? So then, s1 of s on the interval 1, 2 will now be expressed as s1 of x being the same as a1 plus b1 s minus 1 plus c1 s minus 1 squared plus d1 s minus 1 cubed. And s2 of s on the interval 2, 3 will now be the same as s2 of x being the same as a2 plus b2 s minus 2 plus c2 s minus 2 squared plus d2 s minus 2 cubed. So having done this, we can now solve for the coefficients, okay? Now, we already know that for s1 of 1, we have that this is the same as 1. And also, for s1 of 2, we know this is the same as 4. And then we also have for s2 of 2 at the boundary point is the same as 4. And then s2 of 3 is the same as 9. Okay? So once we plug this in, so we now have into this, so we now have s1 of 1 will be the same as a1 plus b1 into bracket 1 minus 1. This is 1, s is 1 minus 1 plus c1 into bracket 1 minus 1 squared plus d1 into bracket 1 minus 1 cubed. So this reduces to 0. 1 minus 1 is 0. 1 minus 1 is 0. So, and this is the same as 1. So that a1 is the same as 1. Now, in the same way, s1 of 2 is the same as 4. So s1 of 2, so which will now be, now we already know that a1 is 1, so that'll be 1 plus b1 into bracket 2, s is now 2, minus 1, plus c1 into bracket 2 minus 1 squared, plus d1 into bracket 2 minus 1 cubed. And here we have 4 will be the same as 1 plus b1 plus C1 plus D1, so that B1 plus C1 plus D1 is equal to 1 minus 3, 1 minus 4, which is equal to 3. So this is another equation. Now, we now have to resolve for these 2 points, for which S2 of 2 is the same as 4 and S2 of 3 is the same as 9. So we'll plug it into this equation, to resolve, to derive the system equation. So for S2 of 2 in 4, we have S2 of 2 to be the same as A2 plus B2, bracket 2 minus 2, plus C2 into bracket 2 minus 2 squared, plus D2 into bracket 2 minus 2 cubed. So this will be the same as 4, so that 2 minus 2 is 0, 2 minus 2 is 0, 2 minus 2 is 0. So A2 is the same as 4. And then the next condition is the same, is for S2 of 3, which is 9, so that S2 of 3 will now be the same as 4 plus B2, 3 minus 2, plus C2, 3 minus 2 squared, plus D2, 3 minus 2 cubed. And this is going to give us 9. So that's 4 plus B2 plus, this is going to be 1. This will also reduce to 1. This will reduce to 1. So that will be 4 plus B2 plus C2 plus D2 is the same as 9. So that B2 plus C2 plus D2 is the same as 5, which is 9 minus 4. So now that we have resolved the function values at the naught point, now we have to consider the first derivative at x being the same as 2, as previously documented. Now, to evaluate the first derivative at s equal to 2, then we have the first derivative S1 of 2 is the same as the first derivative S2 of 2. And this is going to give us S1 of, the first derivative of S1 of x is given as B1 plus 2C1 S minus 1 plus 3D1 S minus 1 squared. And also, the first derivative of S2 of x is the same as B2 plus 2C2 S minus 2 plus 3D2 S minus 2 squared. So now, if we invoke this first time derivative condition, which is the first time derivative continuity condition, then we have that B1, this expression, plus C1 into bracket 2, for which S is 2 minus 1, plus 3D1, 2 minus 1 squared is the same as B2 plus 2C2, 2 minus 2, plus 3D2, 2 minus 2 squared. So this reduces to 0, this reduces to 0, then this goes to 1, and this also goes to 1. So there we now have B1 plus C1 now this is 2C1, not C1, 2C1 and 2C2, yeah. So this will give us 2C1 plus 3D1 will be the same as B2. Here's another system of equation. And now we have to consider the second derivative continuity at s being the same as 2. So that the second derivative of S1 at 2 being the same as second derivative of S2 at 2. And we already know that the second derivative of S1 of S is the same as 2C1 plus 6d1 s minus 1. And the second derivative of s2 of s is the same as 2c2 plus 6d2 s minus 2. So that once we evoke this condition, then we have 2c1 plus 6d1 into bracket 2 minus 1 plus 2c2 plus 6d2 into bracket 2 minus 2. So this reduces to 0, and this reduces to 1. And then we have 2c1 plus 6d1 is the same as 2c2. It's another system of equation. And then the next point is to evaluate the natural spline boundary condition, for which we have at x being the same as 1, the second derivative of s1 of 1 will be the same as 2c1 plus 6d1, 1 minus 1 is equal to 0, right? Based on the boundary condition, and this reduces to 0, 1 minus 1. So 2c1 is the same as 0. So c1 is the same as 0 over 2, which is the same as 0. And also, at x equal to 3, we have the second derivative of s2 of 3 would be 2c2 plus 6d2, 3 minus 2 is the same as 0. So that 2c2 plus 6d2 is the same as 0. And in this case, this implies 2c2 being the same as negative 6d2. So that c2 will be the same as 6d2, negative 6d2 over 2, which is the same as negative 3d2. So c2 is the same as negative 3d2. So now that we have been able to resolve the system of equations, then we could solve for them through substitution. And if we do that, we already know that b1 plus c1 plus d1 is the same as 3, but c1 is the same as 0. So that b1 plus 0 plus d1 is the same as 3. Also, b2 plus c2 plus d2 is the same as 5. We already know this, okay? So that b2 plus 2c1 plus 3d1 is the same as b2. We already know this, but c1 is the same as 0. So once we substitute c1 to 0, so this reduces to 0. So we now have b1 plus 3d1 to be the same as b2. So also, we know that 2c1 plus 6d1 is the same as 2c2, but we already evaluated c1 to be the same as 0. So this knocks off to 0. So we have 6d1 to be the same as 2c2, right? 2c2. And we also know that c2 is the same as negative 3d2, right? So once we plug that in, we have 6d1 to be the same as 2 into bracket, excuse me, 3d2, which would be negative 6d2, 6d1. And then we can as well say that d1 is the same as negative d2, and also d2 is the same as negative d1. And then we know that C2 is the same as negative 3d2, but B1 plus D1 is the same as 3. So that B1 will be the same as 3 minus, that would be minus D1. But if we now put B1 into B1 plus 3D1 equal to B2, so we have 3 minus D1 plus 3D1. So we are plugging this into this, which is equal to B2. So that we have 3 minus D1 plus 3D1 is equal to B2. Here, B2 will be the same as 3 plus 2D1 minus D1 plus 3D1. That will be plus 2D1. Now, we also know that C2 is the same as negative 3D2, and also D1 is the same as negative D2, so that D2 is the same as negative D1. So C2 will be the same as negative 3, negative D1, which will be the same as 3D1. Both B2 plus C2 plus D2 is the same as 5. So now we're going to substitute. I'm going to substitute for B2 being the same as 3 plus 2D1, and then C2 to be the same as 3D1, and then D2 to be the same as negative D1. So in this case, we are going to have 3 plus 2D1 plus 3D1 minus D1 equal to 5. So we can simplify this. That's 2D1 plus 3D1 minus D1 equal to 5. So that'll be 3 plus 2D1 plus this 3D1 minus D1 will be 2D1 equal to 5. That'll be 3 plus 4D1 equal to 5. Then 4D1 equal to 5 minus 3, which is equal to 2. So 4D1 will be equal to 2. So D1 will be 2 over 4, which is 1 over 2. And then D1 is the same as 1 over 2. So now that we've done this, we can back substitute. That is, since D2 is the same as negative D1, then we know that D2 is the same as negative 1/2. But B1 plus D1 is the same as 3. So that B1 will be the same as 3 minus D1, which will be the same as 3 minus 1/2. So that B1 will be the same as 6 minus 2 over 2, no, minus 1. That's 2 in here, 1, then minus 1, which will be 5 over 2. So that B1 is the same as 5 over 2. Okay? And also, we know that B2 is the same as 3 plus 2D1, so that 3 plus 2 into bracket 1/2. So this knocks this off, so it will be 3 plus 1. So B2 is the same as 4. And also C2 is the same as 3D1, which will be 3 times 1/2, which is 3 over 2. So C1 is the same as, let's say C, not E. So C1 is the same as 3 over 2. So far, we have been able to derive the coefficients such that A1 is the same as 1, B1 is the same as 5 over 2, C1 is the same as 0, and D1 is the same as 1 over 2. Also, A2 is the same as 4, B2 is the same as 4, C2 is the same as 3 over 2, and D2 is the same as negative 1/2. So from this, we can substitute into the cubic spline, call that x1 of s is the same as A1 plus B1 s minus 1 plus C1 s minus 1 squared plus D1 s minus 1 cubed. And then S2 of s is the same as A2 plus B2 s minus 2 plus C2 s minus 2 squared plus D2 s minus 2 cubed. So that from this, we now have for S1 of S on the interval of 1, 2, we have S1 of S to be the same as 1 plus 5 over 2, S minus 1, that's B, B1, A1 is 1, B1 is 5 over 2, then plus C1 is 0 times S minus 1 squared plus D1, which is half into bracket S minus 1 cubed. Also, for S2 of S on the interval of 2, 3, will now be S2 of S being the same as A2, which is 4, plus B2, which is 4, into bracket S minus 2, plus C3, which is 3 over 2, S minus 2 squared, minus times plus, as plus will be minus 1/2 S minus 2 cubed. And now we are meant to evaluate P of 2.5. So that's at X equal to 2.5, which is between the points 2, 3. So we'll be using this expression, okay? So S of 2.5 will now be the same as 4 plus 4, right? 2.5 minus 2 plus 3 over 2, 2.5 minus 2 squared, minus 1 over 2, 2.5 minus 2 cubed, which would be 4 plus 4, 0.5 plus 3 over 2, and 0.5 squared, minus 1 over 2, 0.5 cubed. So this would be 4 plus 2 plus 3 over 2 times 0.25 minus 1/2, 0.125. And this is going to give us 6, 4 plus 2, 6, plus 0.375 minus 0.0625. So that S2 of 2.5 is equal to 6.3125. Now, for the Bezier spline, in this case, we have to define some control points, okay? And as such, we call the Bezier spline a parametric curve defined by control points, okay? I think that's about the only difference here, because each cubic Bezier spline, for each of them, the curve is defined by specific control points, okay? And here, we now see, for instance, where we have P0, P1, P2, and P3 control points, then the Bezier spline is given as B of t, 1 minus t cubed, P0 plus 3t, 1 minus t squared, P1, plus 3t squared, 1 minus t, P squared, plus t cubed, P3. Now, this is for all values of t, taking on values from 0 to 1. And in this case, t is a parameter that moves from 0 to 1 across the interval. And if we look up our example, where we have 1, 1, 2, 4, and then 3, 9, for us to be able to evaluate this, now you will recall that we have an interval between 1 and 2. And then we also have another interval between 1 and 3. And between each intervals, we are going to have 4 control points, okay? So it means that between this interval, we're going to have P0, P1, P2, and P3. And now this will be such that we know that this is 1, 1, that is already known, and we also know P3 to be 2, 4. Now, how do we estimate these control points in between? So we take the midpoint first, which is 1.5 and 2.5. So we'll call this the midpoint-based control point. So we want to use this to influence the curvature. And then the next point will be 1.8, 3.5, okay? And then we also have for the second point between 2 and 3, we also have P0, P1, P2, P3. And we know at this point, this is 2, 4. And then at this point, it is 3, 9. So we now estimate for the control point, which will be 2.2. 2.2 for X. And then 5.5. And then we have 2.8 and 7.5. So these are the points we are now going to apply to resolve this polynomial. Okay? And then for the first Bezier curve, that is 1, 2, we are now going to substitute for these values in this expression. Okay? And we do the same for the others. Okay? And once we do this, I think, let me just wipe this so we do it here. So that B1 of t can now take on two values, okay? Because now we have 1, 1, we have 1.5, 2.5,
0.5,
and we have 1.8,
0.8, 3.5,
3.5, and then we have 2, 4, right?
2.4.
So it means we
Yes,
can
sir.
actually split this into two halves of, say, X and Y. So let's assume we split it into two halves. So say for my S of t, so I'm going to have 1 minus t cubed times 1 for X plus 3t into bracket 1 minus t squared times 1.5, then plus 3t squared 1 minus t times 1.8 plus t cubed times P3, which is 2. And then my Y of t will be 1 minus t cubed times 1 plus 3t into bracket 1 minus t squared times 2.5 plus 3t squared 1 minus t times 3.5. T cubed. Oh.
Mute your mic, mute your mic.
Okay. So with this, we can now expand. And once you do this, then you're going to see that X, this is X1, Y1, X1 of t will be the same as 1 plus 1.5t minus 0.6 t squared plus 1.1 t cubed. And then Y1 of t will be the same as 1 plus 4.5 t minus 1.5 t squared plus t cubed, right? So we are going to apply the same for the second point, okay? So you take note of this. And when we do that for the second point, here we have 2, 4, 2.25, 5.5, and then 2.8, 7.5, and then 3.9. So this will give us S of 2t to be the same as 1 minus t cubed times 2 plus 3t, 1 minus t squared times 2.2 plus 3t squared, 1 minus t times 2.8 plus t cubed times 3. And now this will give us 2t plus 0.6t plus 1.2t squared minus 0.8t cubed. Okay. And then we do the same for y of 2t, which will be 1 minus t cubed times 4 plus 3t, 1 minus t squared times 5.5 plus 3t squared, 1 minus t times 7.5 plus t cubed times 9. And this will give us, this is S of 2t, y of 2t will give us 4 plus 4.5t plus 1.5t squared minus t cubed. Now, from the Bezier spline, we can now say that we have for 1, 2, we have S1 of t being the same as 1 plus 1.5t minus 0.6t squared plus 1.1 t cubed, and y1 is the same, y1 of t is the same as 1 plus 4.5t minus 1.5 t squared plus t cubed. And then for the point 2, 3, we now have S2 of t to be the same as 2 plus 0.6t plus 1.2 t squared minus 0.8 t cubed. And then y2 of t will be the same as 4 plus 4.5 plus 1.5 t squared minus t cubed. Now, how do we resolve P of 2.5? Okay, now, in this case, we first have to feed the cubic Bezier spline that connects all the points, okay? That connects 1.1, 11, 24, and 39. Okay, so for us to do that, now you also want to recall that this polynomial P of t is equally the same as 1 minus t squared times p naught plus 2 of t, 1 minus t, then times t times p1 plus t squared p2 all the way, okay? Now, what you will now do is to estimate the value of t, because at this point, you do not have the relationship with respect to s and y, okay? And then we now need to evaluate p at 2.5. So for us to be able to do that, we now have to evaluate the spline at t equal to 2.5. And we'll have to scale this within the range of 0, 1. Because t takes on values from this. So for us to perform the scaling, then we'll have to evaluate t to be the same as s minus s naught over s2 minus s naught, for which we now have 2.5 minus 1 over 3 minus 1. And once we do this, we see that this is 0.75. So we're going to evaluate this at t equal to 0.75. And once we do that, we are going to get the value, okay? And there, when you do that, you see that P at 2.5 is approximately the same as 2.5 and 6.625, okay? And just before we wrap up, because we already moved over time, then we also have the B-Spline, okay, which is more like the Bezier Spline, okay? I don't think we want to resolve this, but I just want you to know that for the cubic B-spline, the curve is defined as C of t, which is the same as sigma n sub I of 3 of t p sub I, for I taking on values from 0 to n. And n sub I of 3 of t is the cubic basis function. Okay, and then p sub I are the control points. Okay, and despite defining a set of control points, in this case, we still have to evaluate the knot vector. Okay, so this is quite rigorous, so we'd rather use MATLAB to resolve this, and for which we say the knot vector t is the same as 0, 0, 0, then we have 1, 2, 2, 2. So we apply this, we apply this in MATLAB, okay? And then we can also evaluate I by the range, okay? So when we consider the polynomial of degree 0, let's say p is the same as 0, the s of I of 0 of t will be the same as 1, such that ti is less than, equal to less than, equal to t sub I plus 1, and then it is 0 otherwise, okay? And then, if, for instance, we now have to consider the polynomial order greater than 0, then we say n sub I of p of t will be the same as t minus t sub I over t sub I plus p minus t sub I, so that n sub I, p minus 1 of t plus t sub I plus p plus 1 minus t is the same as t sub I plus p plus 1 minus t sub I plus 1 times n sub I plus 1 p minus 1 of t, okay? So once we do that, then we can use MATLAB to perform the estimation. And then the last thing I need to mention here is the Hermite before I display the MATLAB coding for all of them. So the Hermite polynomial literally considers not only the function values, but also the derivatives of the data points. And here we see that the polynomial is given as the summation for which I takes on values from 0 to n, h of I of x, y sub I, plus sigma, I taking on values from 0 to n, h of I, steric of s, y prime, which is the derivative. So now the h, I of x, and h of I of s asterisk are the basis functions. Basis functions for interpolation. Okay? And the derivative, the first derivative of y is the derivative of the function x I. Okay? So I think that forms more like the theoretical basis, and I'll just steal a little minute or two from you. Okay. So, okay. Now, this is the MATLAB code for the Lagrange polynomial. So, more like what we already said. So, if I should plot this, let's run. So, that's what we get, exactly what we got for our numerical analysis. And for the Newton divided difference, we also have the same. And that is what we got here too, so which is consistent. Then for the linear spline, Okay, so I need to share the graph. Where's my share button? So this is what we got from the linear. Can you see this plot, please?
Yes,
Yes,
you can
sir.
see it.
Yes, sir.
So this is what I meant when we're talking about the linear spline, and you can see it uses just straight lines. So with this, the approximation is prone to some errors because it does not trail the data point. It does not trail other unknown points, but rather it traces the exact known points. And then so the next is the quadratic spline, for which we define that, and that's what we get. So if we run this, now you see that I can see the quadratic spline trace that curvature, right? For the quadratic spline interpolation. And what else do we have? So for the cubic spline, here we have the code. These are the intervals. And then we have the functions and then the continuity of first derivative interior and the continuity of the second derivative at interior point. And then we have the natural spline boundary condition. Then we solve for the system of equations and then extract the coefficients for each segment. Then we display the coefficients. And in this case, we have the follow to determine which segment to use. Then we calculate the value of the spline. So when we run this, now you see that we have the values, the coefficients are stated as computed, and then the value of the cubic spline is the same as 6.3125 as evaluated. And then we have the Bezier spline. For the Bezier spline, let me pull up the graph. Let's show that. There's my share. So this is what we got for the Bezier spline interpolation. Okay, so it gives an approximation, but close to some linear representation. And then, okay, I think I didn't scroll through the code. This for the Bezier spline interpolation at those points. So the control points were defined, as presented, then, and that's that. Oh, got that. Then what's next? Okay, the Hermite polynomial. So with the Hermite polynomial, we are able to plot the equation, right? Which is x squared. I'm sure you can see that just highlighted. So at times you don't just want to get the points as some values or generate a graph, but you can actually plot the equation. And then that's what we get. I think this is a good place to stop. Hope to see you in our next class.